Good afternoon, I am Mr. Ish. Thank you for watching this video. Thank you for watching my other videos. Thank you for liking and subscribing. I welcome your feedback, your comments, all of that. Today I have a good treat for you here. We're looking at some strategies for rational function integrals. We've never formally looked at rational functions because they are a piece on their own. They're difficult. And there are many ways of you to handle such rational functions. There's not but single way, there are many ways. And each of those ways is rather difficult or complex. I have the word here rules, but it's not rules by the formal sense. It's rules in the sense the conventions we look at in this specific video. One of which is this. Everything over here which I'm showing you, you don't have to worry about proper versus improper because that debate only arise for those integrals which are definite integrals. We're looking at all indefinite integrals. You know, definite integral has a limit, as you know right here, an upper and a lower interval, whereas indefinite integrals don't have such intervals, so you're not worrying about areas below curves or area above curves. So all the discontinuities, infinities, all of that does not matter for these. All the questions we're looking at for rational functions are of this form because you need to learn how to do rational function integrals before you start worrying about something like this. That is, you don't want to compound the process by bringing in this debate over here versus that when you're dealing with rational functions. The other set we want to look at here is the rational function will be something like this. A polynomial in the numerator, right? Some form of a polynomial in the numerator and some form of a polynomial in the denominator. That right there is your rational function. It is something divided by something else, but you have an expression here and an expression here. What we're looking here in terms of the specific strategy, I'm using the abbreviation here, is PLD, polynomial long division, and how that comes to assist you with these rational function integrals. Polynomial long division is an excellent technique for you to handle rational function integrals, and we're looking at integrals of this form. The only rule you need to worry about here is this, that the degree, the highest order degree or exponent must be either the same for both or it must be higher in the numerator. You understand that, right? If you have something like x to the n in the numerator and you have something like x to the m in the denominator, in terms of the exponent over your variable or your expression or whatever, the highest order here, n should be larger than m, or n can be equal to m. You don't want to have a situation here where n is less than m because you don't want to use polynomial long division. You use polynomial long division for these two cases right here, where the highest order degree exponent variable is higher in the numerator than it is in the denominator, or they are both the same. And when we look at each of the three examples in this video, we'll stress that point again. We're looking at three questions in this video. Three rational function integrals will go from easy to hard. But you see, I've used the word here strategies, and I'm only talking about a single strategy, the polynomial long division, because there are other strategies and those are related to partial fractions decomposition. Partial fractions decomposition is a whole other arena of techniques by which you can do these type of questions. Polynomial long division, as I'm going to abbreviate it, PLD, is an excellent spin-off from the partial fraction decomposition technique. It's not true partial fraction decomposition, but it is a form of decomposition technique. And you can use PLD for those instances where you have a polynomial in the numerator, polynomial in the denominator. And now let's look at the exponents. So you see here you have x to the power of 1, here you have x to the power of 1, here at least here n is equal to m. N is your highest order degree in the numerator, m is your highest order degree of exponent in the denominator. N is equal to m, so you can use polynomial long division. Let's do it. You're going to do a polynomial long division. You know how to do that, and that's how you're going to start this out. You're going to see x goes in x one time, and then you're going to multiply this back. You'll have x, here you'll have a 3 and you'll minus it. These will cancel out, and here you'll have a 2 minus 3, which is a minus 1. Now write your answer in the proper format. Your answer is this, 1 plus minus 1 over x plus 3, right? 1 and your remainder. And now this right here is what is exactly going to integrate as your new function converted into this form. The polynomial long division has enabled you to convert a rational function into something which is much easier to handle. And let's handle this. But before we handle this, let's make a little adjustment. You see this minus over here? This minus can very well come right over here and you're looking at that. Now use your properties of integrals and break this up into separate integrals across a minus. You're looking at a 1, which is meaningless, but dx, and then you have this minus integral dx over x plus 3. You don't need to write 1 dx, it's all the same. Now all of this has been converted into what you see right here. The antiderivative here is easy. The antiderivative here is easy. Natural log x plus 3. You know you're looking here at x plus 3 to the power of 1. When you bring it up, you would be looking at x plus 3 to the power of minus 1, right? And dx. And then you can do the natural log on this. And this right here is your answer. And you can always add that and you're done. You see how easy this technique was? Polynomial long division starts it out and you come to your conclusion. You have to just be wary of these rules over here. Alright, let's look at this question. Remember, like I was saying, each question will be slightly harder than the next. And remember, this is just but one way of doing rational functions. It's not the only way, but I'm presenting you a way which can help you simplify these type of procedures. Polynomial long division. Look at the n. The n is the highest order exponent of the variable in the numerator here. N is equal to 2. M is the highest order degree or order of exponents of your variables in your denominator polynomial, and that's a 2. N is equal to m, therefore you can use polynomial long division. You just don't want to do it when the highest order degree of exponent is in the denominator. Then for that you'll have to use partial fractions decomposition. But for these type of cases you can use polynomial long division. Do your division here. And remember, this polynomial long division does not by any means eliminate the need for you to know the varieties of integrals of the functions. You still need to know trigonometric functions or inverse trigonometric or hyperbolics. You have to know all of that because sometimes they can pop up in these type of questions. This is just a technique for handling rational functions. X squared goes in this one time. You multiply this back, you'll have an x squared plus 4, you minus it. This will cancel out. If this does not cancel out, then you made a mistake. This thing should always zero out. The first column must always zero out. 1 minus 4 minus 3. Your answer here is this. This right here is your answer. And then you have a plus, and here's your remainder. 3 over x squared plus 4. But you can of course transpose this minus right over here. And now you're looking at a integral, which is this. This is exactly why I was saying that this polynomial long division by no means exempts you from learning your integrals, because you still have to handle this. When I'm looking at this, you can handle this using trigonometric substitution, or you can handle this using inverse tangent, or bring in the arctan antiderivative, and I've posted videos on how you can handle that. That right there will be a problem for anyone who does not know or recognize that. Anyhow, we're looking here at polynomial long division and rational function integrals. This right here is my new integral, and let's bring it right over here. We're looking at 1 dx minus 3 over x squared plus 4 dx. Now we've just created this space. This first part is easy. This is just going to generate your x antiderivative. This part right here is a challenge. You have to recognize that there is an inverse tangent here hidden in here, or you can do trigonometric substitution, but that'll be longer. If you recognize that there is an inverse tangent function hidden over here, remember the derivative of a tan inverse tangent is always equal to 1 over 1 plus x squared. You see something like 1 over 1 plus x squared. X squared plus 4 is the same thing as you saying 4 plus x squared. But this right here very well mimics something like here. So you should be thinking about arctan or inverse tan coming out of that. So let's do that. And you have to know this technique, and I've posted videos on this. I'll attach some links to the videos I have with regards to this, and you can look at that. You have to make some substitutions over here. U is equal to x over 2, x is equal to 2u. If u is equal to x over 2, x is equal to 2u, you can do du is equal to 1 over 2 dx. See, when you do the derivative on this, du is equal to 1 over 2 dx, dx is equal to 2 du. You have to remember this, you have to remember that, and you have to remember that. And all of that will come into play. We'll set this aside for now, we'll only focus on this. We're looking at, and we'll set the minus aside too, we're looking at 3 over 4 plus x squared dx. We have to work this out, and we're working it out by here. We have here a 3 pushed outside, we have a dx over 4 plus x squared. We have a 3, and now let's bring in this. Dx is equal to 2 du, and then we have a 4 plus x. But x is equal to 2u square, right? And let's bring that 2u square right over there. Now you open this up, you'll have 3 times 2 is a 6 integral du over 4 plus 4u square. Isolate the 4 and bring it out. When you do that, you have 6 integral du, you have 1 plus u square. The 4 has been isolated and has been brought out. You have a 3 over 2 and integral du over 1 plus u squared. This right here is a derivative of an inverse tangent. So by means of the opposite effect, it should bring the inverse tan or the arctan antiderivative. Coming up over here, you'll have 3 over 2 arctan u plus c. Forget the plus c, it's meaningless here. But what's this u? U is right over here. You'll have 3 over 2 arctan x over 2. Remember, the rational function and this polynomial long division technique by no means eliminates all of this. You still have to know how to do all of this, but it's helping you to do this entire procedure in an easy way. We've got our antiderivative over here, and this antiderivative will be attached over here, so I'm going to erase everything and bring it in over here. That's what I have to do, erase it all. This will generate an x, this minus, and all of this coming after that. 3 over 2 arctan x over 2 plus c. And that right there is your final answer. You don't need to do a common denominator here. You can leave this and your answer has been completed and it's done. The hardest part over here was dealing with the antiderivative of this. But for this, you need to recognize you have an inverse tangent or an arctan antiderivative hidden in here, which you have to bring out. Alright, this is our last question and it'll be the most difficult question, but it'll be difficult only mentally, but technically it's actually easy. The reason why I say that is once you learn the technique, even this becomes easy for you. It's an ideal situation here for a polynomial long division. We have a rational function. If you look at the rule I stated at the very beginning, n and m, the highest order degree of exponent that you're seeing in a variable in this polynomial in the numerator is a 3. For that, in the denominator, I'm seeing a 1 over here. N is larger than m, therefore, ideal technique to use long division, and we will. You know the polynomial long division is not hard. I'm just putting this little placeholder over here. Because I have a 3, then I'm going here in terms of exponent to a 1. It's sensible to put a 0x squared. X goes in x cubed, x squared times. You multiply it back. You'll have an x cube and then here you'll have an x square. When you minus this, you'll get a 0 over here. When this zeroes out, you know you're on the right path. Here you'll have a minus x squared plus 2x. X goes in minus x squared minus x times. Multiply it back. Minus x times x is a minus x squared. Minus x times 1 is a minus x minus it. This is cancelling out again, so yep, we're good. Here we have a 3x. Now, let's set everything here in the proper format. X squared minus x is my answer. My remainder is 3x over x plus 1. And technically this has become my new integral. All of that has been converted into that. Now, here's a main important lesson for this specific question. If you look at the remainder over here, this right here is my remainder expression. It is something which can undergo the long division again. N is equal to 1. M is equal to 1, you might as well do another polynomial long division only of this part right here, because dealing with that can be tricky. If you do the polynomial long division, you'll simplify this further, so let's do it. We have 3x plus 0 divided by x plus 1. This is me simplifying this even further. Might as well, because this is an excellent tool for dealing with rational functions. X goes in 3x 3 times. Multiply it back, you have 3x plus 3 minus it. This cancels out and here I get a minus 3. My answer over here is a 3 plus minus 3 over x plus 1. You see this right here is coming out from this right here. And what I can do now is rewrite this entire expression with this part added in to reflect this new item which I just brought out. I have an x squared minus x coming from the original polynomial long division. Now I have a plus 3. Then I have a minus 3 over x plus 1. All of this is dx and all of this is way easier than anything else we have on the board. This right here is easy, easy, easy. This here is easy. It's a rational function, but don't do the polynomial long division because here the degree or order of exponent here in the numerator is a 0 because it's 3x to the power of 0. In the denominator you have x to the power of 1. When m is larger than n, you don't do long division. There's no need to do it, and it's not the convention for which you should do long division. Let's integrate this. It's easy polynomial. X squared will be x cubed over 3. Minus x will be minus x squared over 2, plus 3 is a plus 3x, and this right here is a minus 3 natural log x plus 1, and you know you're done. You can do a common denominator for this part. You'll have a common denominator of 6. 3 goes in 6 2 times, you'll have a 2x cubed. 2 goes in 6 3 times, you'll have a minus 3x squared. 1 goes in 6 times, you'll have a plus 18x. And then keep that separate. Minus 3 natural log x plus 1 plus c. And this is a good answer. And this entire expression right here is a good answer. And you're done. The main gist and theme of this video is we are looking at rational functions, which by the traditional approaches are very difficult to do because they're very messy to do. When you bring in the polynomial long division, and later on when you bring in the partial fractions decomposition technique, which we have to learn, slightly more complex than this, but we can do it, then this technique and that decomposition technique makes rational functions very easy. And with that, I thank you for watching this video. Stay tuned. Have a nice day. Bye.